Okay, in today's video, you're going to be learning about the development of the resting membrane potential. So after watching this video, you should be able to do the following three things. The first is to use Ohm's law to solve for voltage, current, and resistance. This is mainly a review of your physics class, but it's very important for neurophysiology. Second thing that you'll be able to do is calculate the Nernst potential for an ion and determine which way that ion will move under a variety of conditions. And the third thing that you'll learn how to do is to calculate the resting membrane potential using the Goldman equation. From your physics class, you should remember Ohm's law. So Ohm's law is that voltage equals current times resistance. And now you can rearrange this equation any way you like. But just to review, voltage, which is measured in volts, although we'll mostly be talking about voltages in the millivolt range for the cell, but voltage is the electrical potential difference. So it's a difference in charge between one place and the other, and in a way you can think about that as the potential energy that is stored using this charge differential. Current, which is abbreviated as I, is measured in amperes or amps, big letter A. Again, most of the currents we'll be talking about will be in milliamps, and the current is the flow of electric charge from one place to the other. Finally, resistance, or R, is measured in ohms, shown here, and resistance is the opposition to current flow. Resistance and conductance are just the inverse of each other. So resistance equals 1 over the conductance, which is abbreviated as G. And conductance is measured in Siemens. And it's just really the ease of current flow, how easily current can flow from one place to another. Oftentimes that's a little easier to measure. You can also think about conductance in terms of the number of channels that are open at any one time. Later in this lecture, we're going to be talking about the relative conductance, so how many sodium ions flow in relation to potassium ions. Now remember, you can also plug in conductance into Ohm's law, so if V equals I R, you could also write that as voltage equals current over conductance. So if you know one or the other, you can still solve for either voltage or current. The final physics review that I want to go over are capacitors, because our membranes in the cell act as capacitors. So a capacitor is nothing more than something that can separate charge. So there's an insulating material in between, and then positive and negative charges are held apart. Okay? So if you measured the voltage difference with an electrode here, you would see that on this side of the capacitor you're relatively negative versus that side, the other side here, which is relatively positive. The lipid membrane that makes up the cell membrane is a really good capacitor. So facing the outside and inside are your hydrophilic heads, whereas inside is an insulator, the hydrophobic tails. So ions on their own will not be able to cross this membrane. They need channels to be allowed in. So this allows there to be a charge buildup. In the cell, there's relatively more negative ions inside and relatively more positive ions outside. You also have concentration gradients of different cells, with sodium being more concentrated outside and potassium more concentrated inside. In the next few slides, we'll talk about how this charge and concentration gradient has built up and how ions use different channels to flow inside and outside of the membrane. Okay, so remember, lipid bilayer, ions won't just flow straight through, they need channels. This allows it to act as a capacitor to separate the charges from inside and outside. And so, like I said, your cell membrane, so let's just draw a normal cell here, can act as a capacitor, and you can have a buildup of charges. In general, most mammalian cells are relatively more negative than outside, and we can measure this using electrodes. So in this class, I'm often going to draw them like this, a little pointy triangle here. Usually in the lab, this would be a glass pipette pulled really, really thin so the tip can go inside the cell. And inside, you'll have a wire that's hooked up to an amplifier, and I often show a wire coming outside, which is your ground or reference. So, if the electrode is inside, so your active lead, that's the inside wire, is inside, you're measuring the potential inside the cell, so usually it's measured in millivolts, like I said. And so let's say this cell, a typical cell, is reads around minus 60 millivolts. Okay, so the inside of the cell is relatively more negative than the outside. I could just as easily, although not technically as easily, have the active lead on the extracellular fluid and the ground lead inside the cell, and that potential would be measured as a positive 60 millivolts. Okay? But for most of the class, whenever we talk about measuring membrane potentials, we're always going to be referencing inside the cell versus outside the cell. As we just finished discussing, ions need channels to move across the cell membrane. In the next few slides, we're going to be talking about a few of these important channels. And the first is the sodium-potassium ATPase, which is actually a pump. As you remember from physiology, inside of the cell is relatively more negative than outside the cell, and there's relatively more sodium outside the cell than inside, and relatively more potassium inside than outside. And one of the ways that this gradient is established is by the use of the sodium-potassium ATPase pump. So for every 3 sodium ions that it pumps out, it takes in 2 potassium ions. So as you can see, this moves to concentrate potassium inside, sodium outside, and since there are 3 positive ions going out but only 2 coming in, that helps establish the relatively negative inside membrane potential. Now, since you're moving ions against their concentration and electrical gradients, you need energy to make this pump run, and that's in the form of ATP. So throughout your body, you spend a lot of your energy running the sodium-potassium ATPase. About half of the food you eat and a third of the oxygen you breathe goes to fueling the sodium-potassium ATPase. In the brain alone, 10% of your oxygen is necessary to run this pump. So, as you can probably imagine, it's very important for the body to have this relatively negative resting membrane potential. You can use this in the concentration gradient setup to help fuel other pumps. So there's a sodium-hydrogen exchanger in some parts of the body. But since this is neurophysiology, we're going to be focusing mainly on how neurons use differences in ionic concentrations across the membrane to send their signals from one end of the neuron to the other. So the action potential is just opening of channels that allows the cell membrane to depolarize and then repolarize back down to its resting membrane potential. The other channels that are essential to setting up the resting membrane potential are the potassium and sodium leak channels. These channels are always open. They only allow, for instance, if it's a potassium leak channel, they only allow potassium to flow, and it's going to flow down its concentration gradient normally outside the cell, although that really depends on what the membrane potential is, and we'll talk about that later. And sodium leak channels at rest will mostly be allowing sodium in. Now, there aren't an equal number of sodium and potassium leak channels in the cell. There are about 10 times the number of potassium leak channels as there are sodium channels. So, in general, the cell membrane is more permeable to potassium than to sodium. Okay? Another key thing to remember about these leak channels is they're not gated. They're always open, and the ion will just flow down its electrical and chemical gradient, which we'll talk about in a second, how you figure out which way it will flow. So whenever there are channels for an ion, the ion is going to be driven by 2 gradients. Its electrical gradient and its concentration gradient. It has to balance these 2. So, electrical gradient is just like it sounds. If you've got lots of negative charges inside, it's relatively positive outside. If you're a negative ion, you're going to want to go out, right? If you're a positive ion, you're going to want to go in. Okay, you're trying to get that that concentration, that electrical concentration difference to be 0, right? So if right now we're measuring minus 60 millivolts, if we're only caring about the electrical gradient, the negative or positive ions are going to want to move in the direction that will bring that resting membrane potential down towards 0. Okay. Now, an ion is also wanting to move based on its concentration gradient. So, if there's a high concentration of potassium inside the cell, it's going to want to move outside the cell where there's less concentration, where there's a lower concentration of potassium. Okay, but what happens when an ion wants to move, like potassium for instance? It wants to move from our cell outside based on its concentration gradient, but it wants to stay inside based on its electrical gradient, right? It's negative inside, potassium's positive. It wants to stay there to make it 0, but there's lots of potassium inside, so it wants to move out. Figuring out which gradient will win out, or how you balance them, can be determined using the Nernst potential, or the Nernst equation. You may remember the Nernst equation from your chemistry classes. The Nernst equation states that the equilibrium potential of an ion, or E ion, is equal to RT over ZF times the natural log of the concentration of the ion outside over inside. So this equation uses two constants, R, which is the universal gas constant, F, which is the Faraday constant, T is your temperature expressed as degrees Kelvin, Z is the number of elementary charges of the ion. So for instance, Z of sodium would equal +1, Z of chloride would be -1. I'm just going to warn you that in this class we are going to be doing all mental math, no calculators for the most part. So I don't know anyone that can do natural logs in their head, but most people can do log base 10s in their head. So we can use a conversion factor to get from the natural log to the log base 10. And if you assume that we're making our measurements at room temperature, RT over F times the conversion factor equals about positive 60 millivolts. So to rewrite the Nernst equation, we would say that the equilibrium potential of the ion, or E ion, equals 60 millivolts divided by Z of the ion you're trying to figure out times the log base 10 of the concentration of the ion outside over the concentration inside. So let's figure out some of the typical values you might get. If we say that sodium, so we'll find the equilibrium potential of sodium, so that 60 millivolts, its Z is +1, the log of, so there's way more sodium outside than inside, so we'll say we've got about 100 millimolar sodium outside versus about 10 millimolars inside. Now, these are obviously not the exact correct values, but they make the math very easily, and they somewhat approximate how it is in real life. So to solve that, you would get an equilibrium potential for sodium, which would equal 60 millivolts times the log of, when you simplify that down, 10. So the power of 10 that gives you 10 is 1. And so you've got an equilibrium potential for sodium of positive 60 millivolts. Okay, now if we then did the same thing for potassium, again you'd have 60 millivolts over +1 times the log of, well this time we've got very little potassium outside the cell, so we'll say 10 millimolars, and a lot inside, we'll say 100 millimolars. Again, these are approximate values, they're pretty close. And now you get your equilibrium potential to be 60 millivolts times the log of 1/10, and the power of 10 that gives you 1/10 is -1, so now you've got an equilibrium potential for potassium of -60 millivolts. Now that we've calculated the Nernst potential for our ions of interest, we can start to figure out which way ions would move through the passive leak channels that are always open, or other channels that will open throughout the course of an action potential. So let's say we have a membrane or a cell neuron sitting here at a resting membrane potential of minus 48 millivolts. In the next few slides, we can actually calculate this for our example. And we've just calculated that the equilibrium potential of sodium equals 60 millivolts. In this example, we had about 100 millimolar of sodium outside, 10 millimolar of sodium inside. So now, which way will sodium want to move? If sodium had its way, and the only thing that mattered was if only channels to sodium were open, it would want the resting membrane potential to sit at positive 60 millivolts. Okay? So we know that the resting membrane potential is minus 48. Sodium is a positive ion. To bring that membrane potential up towards positive 60 millivolts, sodium would have to move inside the cell. Okay? By doing so, it would bring in its positive charge and move this membrane potential towards the equilibrium potential for sodium. Now, sodium's a pretty easy case because it's moving inside the cell both with its concentration gradient. There's lots of sodium outside, 100 millimolars, very little inside, 10 millimolars. And the inside of the cell is relatively negative. Sodium's a positive ion, so it's going down its electrical gradient as well. So if I were to ask you if sodium was moving with its concentration gradient, you would say yes. Sodium's moving with the concentration gradient, and it's also moving with the electrical gradient. Okay? So that's pretty simple. Your leak channels for sodium's going to want to leak into the cell. Now, a little harder case is potassium. So we just said that the equilibrium potential for potassium is minus 60 millivolts. Again, we've got our neuron here. It's sitting at minus 48 millivolts. Okay, so if only potassium could move, it would want to bring that membrane potential more negative towards minus 60. Since potassium is a positive ion, to make the inside of the membrane more negative, it would have to move outside the cell. Okay, so now you might want to pause this video and try to figure out if potassium is moving with its electrical or with its chemical, or both, in terms of its gradients. So, potassium, there's lots inside, 100 millimolars inside, 10 millimolars outside. Okay, so potassium is moving with its concentration gradient. It's going from high to low, but the inside of the cell is relatively negative, outside is relatively more positive. Potassium is a positive ion, so it's moving against its against its electrical gradient. Okay, so in general, ions have to move with at least one of its gradients, and the Nernst potential helps you figure out which one wins if they're opposing. Okay, so in potassium's case, the concentration gradient is going to win out over the electrical gradient. Now in your problem sets, we're going to have a bunch of different examples with made-up ions, and so you really want to test yourself and make sure that you can figure out, by calculating the Nernst potential, where that ion is going to move if you opened up some channels. In the last slide, I told you what the resting membrane potential was. I told you it was minus 48 millivolts. Well, you can actually calculate this membrane potential for yourself using the Goldman equation. In some books, you might also see it referred to as the Goldman-Hodgkin-Katz, or GHK equation. So the Goldman equation tells you that the membrane potential, which is usually either written as EM or VM, either way, is equal to the relative conductance of all the ions you care about times their equilibrium potentials. So you've got the relative conductance of potassium times its equilibrium potential added to the relative conductance of sodium times its equilibrium potential. So to calculate an exact, precise resting membrane potential, you'd also have to take into account other ions like chloride, but the major drivers of resting membrane potential are potassium and sodium, and they'll be the only ones we care about in this class. So, now conductance, it's usually expressed as a relative conductance, and I told you before that there are many more leak channels for potassium than there are for sodium. So at rest, the relative conductance for potassium is much higher than sodium. It's about, I said before, 10 to 1, but to make our math a little easier, we'll say that the conductance of potassium equals 9, conductance of sodium equals 10, so that means the relative conductance of potassium would be 9/10, relative conductance of sodium would be 1/10. So now let's actually calculate this, that you believe me. So if we say that the membrane potential equals, again, relative conductance of potassium, so we said that was 9/10, times its equilibrium potential of minus 60 millivolts. Then you add that to the relative conductance of sodium, which is 1/10, times its equilibrium potential of 60 millivolts. Okay, now this is just simple math, so you've got minus 54 millivolts added to 6 millivolts, and voila, you've got your minus 48 millivolt resting membrane potential that I just told you before. So now you should be able to figure out the membrane potential at rest, given Nernst potentials or starting concentrations, or you can also calculate it at various times of an action potential, given changing relative conductances, or with made-up ions that I'll give you on your problem set. So make sure you test yourself on this and feel very comfortable with it. That concludes this video on the resting membrane potential. Make sure you test yourself with the online quiz and problem set and make up your own problems to figure out how membrane potential would change if you change the starting concentrations of one ion or another, opened more channels, had crazy different ions. Just make sure you really understand this because this forms the basis of the rest of this section.